Okay then. Well, it appears that we are live. Mark, how are you doing? It is episode 19 of Uplink. We've had a little break, haven't we, Mark? But you know, it's not to say that we haven't been busy in the background. And I've got to say, what a great note to, I guess, recommence this journey. On the journey that was, I guess, documented beautifully yesterday. Tell us a little bit about Solar Orbiter and our trip to the sun.
Indeed, yeah, it's been a little bit of a break, as you say, and people as people have been kind of, some people be going back to work as the situation has been changing in the last few months. It impacted us in trying to put the schedule together. But it's interesting that during this entire period, we've been commissioning a whole new spacecraft in the solar system, Solar Orbiter. So Solar Orbiter is a joint European Space Agency and NASA mission to explore the sun from close up. In partnership with other observatories. It's been in development a long time, but it was launched in February from Cape Canaveral. So NASA were responsible for the launch, and ESA built the spacecraft and most of the instruments. And then the coronavirus pandemic hit us, and so that brought into question, how will we actually do what we do, which is commission a spacecraft, make sure everything's working once it's in orbit. And there was actually a brief moment where Solar Orbiter and a few of the other missions in the solar system were temporarily put into hibernation, let's say. They weren't shut down, but they were not being accessed daily because there was the possibility of coronavirus infection at our mission control, ESOC in Darmstadt. But what's brilliant is that the teams have come together over that period, and most of the commissioning of it has been done from home. So it hasn't actually been done in the normal places, in the normal institutes and offices. And what we saw yesterday was vindication of that, because the first images that came back, they were taken a few weeks ago as on its first closest approach to the sun, at about half the distance from the sun that the Earth is. So people have been looking at that, and they've been very excited by what they've seen, because this is only commissioning. This is only the beginning. And yet already, as our guest today will explain, they found some interesting hints of new science.
For the benefit of everyone who's watching and myself as well, you've used a word a few times. What do you mean when you say commissioning exactly? Is that turning the ignition?
Well, the ignition, if you like, is the launch. So that's getting off the ground and getting either into orbit or with Solar Orbiter on its way to several flybys at Venus, one at the Earth. So that's the ignition part. But, it's like turning the radio on and tuning into the right radio station. And we all know there's right and wrong radio stations to be listening to when you're on a road trip. And in fact, if you like to sort of continue that metaphor, I think I've probably painted myself in a corner here by starting that. There's 10 radios on simultaneously. There's lots of different instruments on board, some which are taking pictures of the sun from a distance, some of which are feeling the environment around, magnetic fields, particles. And this is all at the same time as you're learning to operate the spacecraft, making sure that it can turn in the right positions to keep the sun in one place and the instruments pointing where they need to point. So we call that commissioning. It's the period during which we check everything out, make sure what we thought would happen when it went into space actually happens. And sometimes it doesn't, sometimes there's a glitch here or a parameter you need to tweak in software. So it's a learning process. But at the end of that, you basically say it's all ready. And then the project handed over, the project that built it, handed over to the scientists and the mission operators. And that happened as well last week. That moment occurred where the spacecraft was declared ready for science operations. It's not fully in the right position for that because it's in a cruise phase now. It's not in its full science orbit, but some of the instruments are on already working day and night. So, well, actually, it's all daytime in space where this is, it's looking at the sun, it's always daytime.
Indeed. Well, it's that's a very good point, actually. Easy to forget. Well, perhaps no one more qualified in the world to tell us this story than Miho and Daniel, who we were just bringing in, to kind of, I guess, give depth and background to this remarkable achievement. And I'm just going to do a bit of commissioning myself right now. I'm just going to double check with Miho and Daniel just to check, are you guys receiving?
Yes.
Yes.
So let me do the brief introduction, because we would have done it before we brought you in, but I was gabbing on about other stuff. So Daniel, you see here, Daniel Müller is Easter staff. He must be because he's wearing the same polo shirt as me. We're all in uniform today. Daniel's the project scientist for the Solar Orbiter mission. Is a solar physicist, has worked on missions, previous missions like SOHO, was based at NASA Goddard Space Flight Center for a number of years and has been on Solar Orbiter for the last decade or so. And Miho Janvier is a solar scientist working at the Institute of Astrophysics in Paris. And is deputy project scientist for one of the science instruments, SPICE, and is also a co-investigator, so a scientist involved in one of the others. And so we have a great team who can tell us all about, how we got this machine into space, what it's designed to do, and what we're already seeing from some of the results that we had back yesterday. So welcome, Daniel, Miho.
Thank you, Mark.
Welcome to the show. And I've got to start with probably the most obvious question I could think of, which is usually a kind of difficult to think up, but in this case, it's I have to say, didn't anyone ever tell you you're not supposed to stare at the sun? Yeah, am I right? Obviously, I say it in jest, but I think for many people, they probably learned more yesterday about what the sun actually looks like than for many have ever seen in their lifetime. Because the beauty of these photos, the power and what they mean. But do you feel that perhaps there's almost like a taken for grantedness about the fact that we know a lot about our nearest star? Because it struck me as a lot of this news was coming out yesterday, there's still a lot that we don't know.
You're absolutely right. And this is clearly something that I learned when I started doing, let's say, outreach activities when I was based in the US, especially with schools, because I would naturally say, well, when you look at the sun, you see this and that. And then I was told, no, you should tell them they shall never look at the sun with unprotected eyes, and give them the entire rundown of safety measures. And that's actually true. So sometimes I forget, and because I do differentiate between looking at the sun, let's say, professionally with telescopes, and of course, not really staring into the bright object that I see on the sky on a lucky day with blue sky in Holland.
That's not today, I think, right?
Well, I'm looking into blue sky here. So right here on the coast, it is blue right now.
Yeah, he's a couple of kilometers closer to the beach than I am. So
very lucky.
But yeah, I would like to jump in and what you said, Alex, about the fact that we take it for granted. And when you think about the celestial objects that humankind has witnessed, the sun and the moon are the most common ones. So you would think that by this time we would know a lot about the sun, and we do, but there's still a lot of things that we don't know. And that's what, for me, is quite fascinating about this star.
Yeah.
So if I look in the background, of course, both of you have images of the sun there, and it's nothing that the human eye would see like that, right? I mean, it's not only, again, humans are not particularly well adapted to staring at that bright object, but we're not just kind of dimming it down and looking at it in the way that humans would look, right? There's much more to be seen by expanding wavelength coverage, for example.
Exactly, and so we, with our human eyes, we only see a certain amount of, certain range of wavelengths that the light transports from the sun, but we don't see UV light and X-rays. And so what you see in the background here is the sun that is seen in extreme ultraviolet. So even if we could stare at the sun, we wouldn't see all the details that we can actually see in UV light.
And speaking of those details, I mean, there were some remarkable revelations already, being revealed, yesterday. So tell us about ghosts, campfires, and some of the details that have emerged, because I'm absolutely intrigued to think that we're literally seeing some of these things for the very first time.
Right. So what we were looking at yesterday were the first set of test images from the Extreme Ultraviolet Imaging Telescope on Solar Orbiter. So that's a decently sized optical telescope. Like Miho said, it doesn't observe the sun in visible light, but really about a factor of 30 shorter in wavelength than blue light, roughly. And so what it shows is a hot material in the sun's, let's say, atmosphere that we call the corona, that is on the order of 1,000,000 degrees centigrade. And what really stunned everyone is that given that such a telescope is a complex machine, it's a one-off, it doesn't have, let's say, a simple user mode like a camera on a mobile phone, that despite all these caveats, the first test images turned out to be incredibly sharp, everything in focus, most parameters just worked out of the box. And that was maybe just luck to some extent and proper configuration from engineers, of course, in addition on the ground, but it really reveals, let's say, a new scale. And as the PI, David Barchmans, was saying yesterday, is to some extent that the sun is exhibiting scale-free phenomena. So that may be a bit too technical a term, but what it means is as you go to smaller and smaller scales, you see details at smaller levels, a little bit like a fractal. And that is clearly not entirely surprising because this is physics. I mean, you don't expect things to suddenly become rock solid big blocks of something at some scale, but it's really eye-opening for us because it really means every time we push the envelope and go to higher resolution, we learn new things and we give them funny names just because we don't know yet what they really are.
So let's step back for a second, because some of the audience watching, may just think of the sun as a thing which is burning. I mean, some people say, how can you have a campfire on the surface of something that's already, 5,500 degrees? Of course, as you said, it's a name invented. But just, take us very briefly through, what the sun actually is. And also, the sense of scales that we're looking at. How big is that object? And of course, some of this stuff I know, some of it I don't know so well, but the very fact that actually the burning part of the sun is not what we see on the surface, where the actual nuclear fusion is going on, is just a very small part of the volume in the center. The rest of it's just a blanket, basically insulating it and letting the energy leak out slowly. So between the pair of you, tell us what the sun actually is.
Okay. So maybe I'll take the initial part, and then Miho can extend that further. So ultimately, the sun is a ball of hot ionized gas. So it's largely hydrogen and helium, so the two lightest elements. And what is happening in the innermost 2% of the radius is this nuclear fusion that you mentioned, Mark, where under immense pressure and at high temperatures beyond 50 million degrees Kelvin, these hydrogen atoms, or effectively protons, are actually pushed together and they are fused, making helium out of hydrogen. And that fusion creates energy that in, let's say, the inner part of the sun is transported by means of radiation. So it's just like photons trying to make their way out. And it's not easy because they constantly hit another particle and get absorbed and re-emitted. So it takes on the order of 100,000 years for a poor photon or their descendants to get out of the sun. The outer part, roughly the outer 30%, is what we call a convective envelope, and that is where convection, what you know from, let's say, your convection oven, or let's say air and other media, or boiling pot of water, material moves around, and heat is transported by moving it around. And this is where we get from temperatures of a few million degrees down to what we see in visible light at the surface of roughly 5,500 degrees. And I should give you a scale. So the entire sun has a radius of 700,000 kilometers. So if you put the Earth as a planet next to each other, you would fit 109 times our planet along the waist of the sun. So that is to give you a scale. And and once you're at this cool surface, then something really remarkable happens, and that's something that maybe Miho can tell you a bit more about.
Yeah, sure. So I guess in everyday life, what you would see as physics happening in everyday life is that every time you get away from a source of heat, generally the temperature drops. So that what happens, for example, if you're near a radiator and you get away from the radiator, the temperatures are supposed to drop. So if you compare the temperature of the center of the sun, which is around, as Daniel said, around 15 million Kelvin, you get to the surface of the sun, it's around 6,000 Kelvin. And then you enter the atmosphere of the sun, where we are expecting the temperatures to drop even further, but that doesn't happen. On the contrary, the temperatures start to rise again. all the way up to, again, a few millions Kelvin. And so that's one of the great mysteries of the sun. That's what we call the coronal heating problem. So the corona is the sun's atmosphere. And it's a big question at the moment to know, why is the sun's atmosphere so hot when the laws of thermodynamics are saying that normally the temperature should drop? And so what the pictures have revealed yesterday, those campfires might be one of the solutions to this coronal heating problem. So basically it would be kind of little explosions, what we call flares, happening all over the sun. And those explosions could be the reason why the sun's atmosphere is so hot.
So could I ask just, I mean, I think one of the things that is frequently missed and frequently blows my mind is the scale of what we're talking about here. So when you say campfires, I guess you're saying something that's about that big, am I right?
That's a very good question, Alex. And I've been asked that more than once since yesterday. So how big is that? What we are seeing is simply, let's say, the scale of the pixels of our detector. So it turns out that the optical quality of this telescope is really good. So the images are not limited by the optics of the telescope, but right now by the scale of the detector. So it's a detector similar in type to what you have nowadays in a compact camera or even camera on the mobile phone. And it has 4 megapixels, so that doesn't really blow your socks off if you're a teenager and want to get a new mobile phone. But they are very, let's say, specialized detectors that are radiation hard and sensitized for UV light. And what we see here, this emission from the super hot plasma, comes actually from a little sprinkling of chemical elements that are not hydrogen or helium, but in fact, in this case, iron. So there are a little sprinkling of iron ions in the sun, and they get stripped off many of their electrons. So in this case, it's 8 to 9 times ionized iron, and that has, let's say, emission in this part of the UV light. When it gets excited by moving around and then gets de-excited, it emits this light. So this is what we are seeing. And we can then, let's say, involve mathematical models and theories about how this magnetic field reconfigures. And the bottom line is ultimately it gets rid of excess energy that was previously stored in terms of, let's say, tension of the magnetic field. And once it gets into a more relaxed state, it gets rid of that energy, and a part of it heats the plasma locally. So it brightens up, and that's what we see.
So the one thing which, just going back to the nuclear fusion part, I mean, people sort of think, oh, it's amazing the amount of energy being produced. The fact that I've always loved is that actually your body per cubic centimeter produces more energy than the sun does, right? The sun is an incredibly bad nuclear fusion reactor in many ways. I mean, that's a good thing, because otherwise it wouldn't live very long. If it was a good one, it would all be gone. So this reaction, this fusion of hydrogen to helium is incredibly bad, but just enough to keep us going, right?
Absolutely. And once, for, let's say, a talk to amateur astronomers, I just looked for something that I could relate it to. And something I found, I wasn't really sure if they would like it, but I said, look, it's a bit like the energy density coming out of a compostation heap in your garden. It doesn't really, let's say, make the sun sound very sexy when you talk about it that way, but it shows you the power of scales. I mean, just imagine you had this humongous heap in your backyard, and suddenly you could really power the universe.
Yeah. So then you briefly mentioned it, and Miho, if we come back to you, this business, of course, we're not just looking at the sun from a distance, because when the photons, the light, comes away and travels to Earth in just 8 minutes, there's particles. They come out in the solar wind, and it's all, tangled up with the magnetic fields, which are not just local to the surface of the sun, creating these loops and flares, but the magnetic field expands out through the whole solar system. So give us a bit of perspective, because solar orbit is not just about taking pictures of the sun; it's about feeling and sensing the sun from a distance as well. Why is that important that we do that closer to the sun than we've done it before?
Yeah, so I guess what you said about Solar Orbiter being for me, quite a fascinating mission in the sense that it has all these 10 instruments and 6 of them are telescopes, so what we call remote sensing instruments, so they see the sun from afar. And then the 4 others are in situ instruments that are, as you said, sensing the particles and the magnetic field around the spacecraft. And that, as you also said, the magnetic field extends all the way up to the end of the solar system. I like to call it like a magnetic bubble or cocoon in which we all base with all the planets of the solar system base. But the thing is, so we know that the sun's influence goes all the way to the boundaries of the solar system. But by the time the particles and the magnetic fields travel away from the sun, they kind of have interacted with other magnetic fields, for example, structures that are coming out from the sun. Particles might have moved in a different direction. So by looking at closer to the sun, it's kind of looking at the stream close to the source of the stream. So where we are at Earth, we are kind of down the stream and we receive those particles, we receive those magnetic fields. So we kind of know what happens around the Earth. But between the sun and the Earth, there are a lot of things that are going on. And so by getting closer to the sun, we kind of look at the pristine state of the solar wind and the particles, the magnetic fields. So that's why we want to get closer, to really get kind of a missing puzzle in the whole sequence of what happens at the sun and what happens much further in the solar system.
So this is the thing where, if I could just interrupt very quickly, Mark, I'm very sorry. But I just wanted to, if we could just hit pause there for a moment, because to kind of reassert what we talked about, Miho. So there is a gigantic flaming nuclear reaction happening in the center of our solar system, and we are sending something to get closer to it, right? I mean, literally this, topic for today is, the sun up close. Everything about that seems counterintuitive, trying to get, so I wondered if we could briefly talk about the actual, the spacecraft itself, and, what it actually requires, because looking directly into, the sun's corona, that's not just a little lens filter, is it? I wondered about the actual craft itself, because it just seems like such a remarkable feat of engineering.
You're absolutely right, Alex. That is really, a real engineering achievement, and probably as a the scientific community sometimes tends to forget about the machine behind it as soon as it starts producing data. I myself included, when I first started about 20 years ago, I just thought that this was just something simple that someone put together and then it gives you the data, and this is what really counts. But in fact, really many years of engineering manpower went into building a machine that works, and not only from, let's say, the protection perspective, but also in terms of the compatibility of the instruments with each other. It's really like a bit like going on a bus tour with a bunch of tourists that all have very different needs and demands. So you have these telescopes that ideally just want to, let's say, move between different filters for different parts of the spectrum all the time. They want to even process their data on their little computers on board. And then there are these, I would say, let's say, neurotic passengers that always want, let's say, noise canceling headphones because they want to really detect the nuances of the road they're traveling on and measure minuscule fields and particle fluxes. And they get disturbed by these, let's say, noisy cameras. And that's really something that took us a lot of effort to make them a habitat in which they can all coexist. And luckily, we have a fantastic magnetometer that was built to really high specification. And we are really happy that also the PI is amazed about the quality of data that he's getting. So we have this roughly 4-meter boom behind the spacecraft, where we put let's say, the most sensitive passengers, the solar wind analyzer, a plasma, a magnetometer from the radio and plasma wave suite, and the vector magnetometer that was built in Imperial College in London, to keep them as far away as possible from the rest of the spacecraft. But yes, ultimately they're all on a relatively small ride, and it had to be done so that they all survive the intense radiation. They also do not get too cold, because as soon as you are not seeing the sun anymore, you are just in interplanetary space. It will just get extremely cold, on the order of -90 degrees centigrade. So even that is something you need to think about when you design your instruments.
Sorry, Miho, go ahead, Miho.
If I can add something also about the mission, for me, what was really interesting at the beginning when I joined the mission was the complexity also of the orbits, in the sense that I guess so far I've mostly used data from spacecraft that are positioned in a stable orbit, very close to the Earth. So we kind of get the data very quickly. But Solar Orbiter goes really, really far away from the Earth. So there's also a lot of complexity in terms of how much data can you store on the spacecraft, and when to use the best time to dump all this data back to Earth whenever the spacecraft gets closer to Earth. So in a way, for me, it was a different way of doing solar observations than what I was used to.
So let's dig in on that a little bit, because I think that's something which, you know, people don't really appreciate. We talked about it, you know, before we came live on air. You know, people are kind of used to getting data back from SOHO and Solar Dynamics Observatory and other solar missions in low Earth orbit almost instantaneously. They're just sort of monitoring webcams looking at the sun. But Solar Orbiter is not like that at all. It's a complex machine, as Daniel said. Some instruments can be on while others have to be off. Pointing isn't always the same for all the instruments. But this business about data rates is really important, right? Because it's not just sitting next to us. We don't get the data back in real time. So Daniel, tell us, you know, we've got memory storage on board. Data are taken at certain points in the orbit perihelion, getting close to the sun, but they may not come back for months or weeks and months, depending on exactly the rest of the orbit.
That's exactly right. And so that requires a lot more planning on all fronts than for other missions. And so to some extent, at some point, I mean, people were in such an agony that they thought, well, maybe this should just be 2 missions. And of course, I mean, if you talk to the funding agencies, they said, well, you must be kidding. I mean, you're lucky to get 1 mission. Now, don't start talking about 2. But indeed, I mean, if you compare to SDO is in geostationary orbit. They have a dedicated ground-link, downlink antenna that they see and talk to every single day. And they download more than a terabyte of data every single day. And they take pictures of super high resolution every 10 seconds. And that's clearly impossible to do when you're out in interplanetary space. And so I remember many years ago having the first discussions with Paolo Ferri from ESOC, who's a real veteran in operating spacecraft. And he said, well, it's too bad that we can't fly these interplanetary missions a bit closer to home, because it would really help. and I like that. And it's really, I mean, people understand that if you fly to Pluto, then, well, yes, it's far away and you don't get a lot of data back. But they got used to getting a lot of data from solar missions. So having to deal with, let's say, a real constraint that you have to store your data on the spacecraft in memory for up to half a year is something that people don't like particularly, and neither do I. But we just really need to work with it and let's say plan observations cautiously. And we revised our entire orbit planning because we realized that we could tweak the orbit in a way that we would achieve the same goals in terms of distance and ultimately polar perspective in different ways that enables us to get a lot more data down. Because as soon as you start getting closer to the Earth, your data downlink rate goes up quadratically with closeness to Earth. And that really makes a difference. So if you can once in a while just get to half the distance between Sun and Earth, you can dump all your data that you've accumulated in a matter of days. And that really helps. And so that's what we've put in. Also, I have to say, thanks to the, let's say, spare time effort of a dedicated colleague, Yves Langevin, who just does orbits just for fun on weekends. And so we talked to him and said, well, Yves, I mean, if you think this is fun, maybe you could have a look. Maybe we can do this better. And he did, and ultimately came up with a trajectory that was, let's say, the best of both worlds. And yeah, that's the trajectory we're on now.
So let's, I was going to go to something else, but let's stick with that for another second, because I think it's really important people realize we just don't kind of go from the Earth and go to this place near the sun and then start taking data. It's nothing like that. What Solar Orbiter is doing is an incredibly complex trajectory. So talk us through between you about, you know, obviously there's gravity assists as well, which help us move in slowly. We're not just sort of falling towards the sun. In fact, it's difficult to get towards the sun, right? Because you've got to get rid of energy somehow. But also this business of getting lifted up to look look down on the poles, which I think is something it's novel, of course. It'll be the first time we've seen really good pictures looking down on the pole. So Miho, let's start with you. I mean, this is a test now. So talk us about gravity assist, how this actually works through. How
Yes.
What are we doing?
So gravity assist maneuvers are basically maneuvers that bring a spacecraft close to a planet, and there's an exchange of momentum, so that basically either you can accelerate or you can slow down a spacecraft depending on the angle of attack of the planet. So this time we're using both the Earth and Venus in order to get closer to the sun and also to get out of the ecliptic plane. So the ecliptic plane is the plane in which the solar system planets are orbiting, so the Earth, Venus, Mercury, etc. So we're going to use Venus in order to get out of this plane, and for the first time, taking pictures of the poles of the sun. And for me, that's really, really exciting because we've never seen them. But it's not just for me. I guess for the whole community, it's really exciting to have the first pictures of the poles of the sun. So yeah, as you said, it's difficult, but it's not new in the sense that planetary exploration, so missions that are dedicated for the exploration of planets of the solar system, have been using gravity assist maneuvers to get closer to the planets. For example, the Voyager missions, but also Cassini and others. But again, for me, what's fascinating is that we are using it for a solar physics mission, solar and heliophysics mission. So I'll leave the details to
I was intrigued. The one thing you said yesterday, Daniel, we've got one Earth flyby in that whole business. As you said, if we always stayed a long way from the Earth, we wouldn't get data back. So we're not on a circular orbit at all. It's highly elliptical. We go in closer to the sun and then come back out again. But we do have this Earth maneuver, and I must admit I didn't know the numbers. So tell us, how close that particular Earth maneuver is. Pretty close, right?
Right. So that particular Earth maneuver is the third of our gravitational slingshot maneuvers. It will happen in late November next year. After 2 times flying by Venus, we'll pass by Earth, and the altitude is just 440 kilometers. So that's roughly the distance or flight height of the ISS. Yeah. So it's really amazingly close. It's probably as close as you can safely go on such a maneuver, but it also really means that the operations engineers really need to have their numbers precisely right to know exactly when to fire the thrusters, because there's no turning back. I mean, if you miss that turn, then you're going somewhere else and not where you wanted to go. But this is what they do for a living, so we have 100% trust that it will work. But it is quite amazing.
I mean, I was also, we've talked about this we've talked about Bepi Colombo, for example. Bepi is coming back, it's had an Earth flyby, it has a Venus flyby later this year, and then Solar Orbiter has one. But both Bepi and Solo come close to the Earth within about 2 or 3 days of each other next August, right? At Venus, not at the Earth. Mm. So, it's going to be a busy time with these two teams trying to work out exactly where their spacecraft are and everything else.
Yes.
So the Venus flybys, there's loads of them as well, right? And we have up to 7 during the mission.
That's exactly right. And so in a way, it's a little bit like a solar system billiard game where you try to really make use of the few planets that we have flying around, because as Miho said, it's an exchange of momentum. So you need massive bodies that effectively are unfazed by a tiny object flying past, but it really makes a big difference for that tiny object, our satellite. And Venus has, let's say, a orbital period of 225 days compared to, let's say, our Earth year of 365. And Solar Orbiter has a trajectory, let's say, an orbital period of between 150 and 180 days. And it changes throughout the mission. But the name of the game is really to make sure that you are in a, let's say, ratio of your orbits with Venus that is in resonance, meaning, let's say, 3 to 2, 4 to 3, so that every small number of orbits you meet Venus again, because that's the only way you can get another, let's say, lift from Venus to either get closer or get out of the ecliptic plane.
And I'll just add something from a scientific point of view. What is quite interesting as well is by doing flybys, so not for all the missions, but for some missions, it also gives us an opportunity to do science on other objects that were not supposed to be the main target of these missions. So for example, for Bepi Colombo is headed towards Mercury, but by doing this flyby near Venus, we also collect data around the Venus environment, and therefore that provides data for people who are working on Venus. So I like to have this kind of working together with different communities in space physics.
It's kind of all the more remarkable that this has all happened in 2020. Of all of the years. Daniel, you said something really interesting. Scientists tend to overlook the instrument once it begins kind of sending data back, right? It's interesting, but stepping back from this endeavor just a couple more steps, it's also apparent the human factor as well, because down here on Earth, it's been an adverse circumstance in which to conduct, as Mark was saying earlier, to commission, I guess the results of which we were seeing yesterday. So how has this been affected by COVID? How did the team behind Solar Orbiter have to adapt to this new reality?
That was indeed the biggest challenge of this year. And clearly, I mean, what we thought were challenges in January are nothing compared to what we had to look at in late March. So in late January, we brought over 1,000 European colleagues and their families and friends over to Cape Canaveral to watch the launch. And that was, let's say, a challenge in terms of logistics and getting all these visitors accredited to an Air Force facility to watch the launch. But ultimately, it was just a very nice experience for all these people to see that this is actually getting real and seeing a tiny spacecraft on a big rocket launching into the night sky. So that was fantastic. And I believe back then, I mean, we got all disinfectants and made sure that we washed our hands, but this was something happening really far away, not really affecting us in any way. And then a few weeks later, when the instruments started their commissioning activities, meaning the one by one calibration and setting up the instruments, this is a period where you really huddle in the control room in Darmstadt in Germany with the operations engineers and the instrument teams who have built the instrument and know how to operate them in detail. And they say, okay, now do this, and now tell me what you see. And now, based on that, we do something else. And that is exactly the time when, let's say, the first real worrying signs popped up in Italy. And then ESA had to adapt to, let's say, these regulations and say, look, if there's anyone from northern Italy, they can no longer come in. And then it turned out to be our Italian-led instrument that had just started their work in Darmstadt. And they said, oh, well, we don't know how to do it because half of our team are from northern Italy, but we need them. And they very professionally adapted and said, look, we understand it's out of everyone's control. And they started doing that in part remotely, in part still on site. But within a matter of days, things went downhill very fast because ultimately a colleague at the control center was detected positive with the virus. And then just to keep people safe, they effectively had to close down the entire control center physically. And the instruments were put into hibernation. And that really felt terrible because essentially they were not really checked out. And it was absolutely not clear how long that would take. We knew that the instruments could deal with that because they have been designed to, let's say, be left alone in periods when we are far away and behind the sun and out of contact. So we knew that would work, but we knew that these critical early activities depend on interactivity. This means sending commands to the spacecraft and the instruments, getting the response, and then acting accordingly. And we knew the spacecraft would not slow down, but instead really accelerate further from Earth. And instead of waiting half a minute for a signal, you would suddenly have to wait several minutes until you got even the confirmation that the command was received. And that is really, I think, what impressed me most on a human level, that people said, okay, this is the situation, we'll somehow make it work. And on a let's say agency level, the control center in Darmstadt managed to already after less than 2 weeks open up in a very, let's say, safe setting, allowing only a minimal number of people and doing as much as possible from outside. But one should remember that these are, let's say, deep space operations where so far people said it's not safe to do this from your home. You shouldn't even be trying. You shouldn't set up, let's say, a remote connection. This is something you have to do in this location. And except for, let's say, small contingencies, there was no real plan for what you do in cases like that. So everything really had to be decided at short notice, but people resorted to a combination of high and low tech solutions, from using, let's say, multiple web conferencing tools in parallel, down to just really pointing a webcam at some computer screen that didn't have a connection to the outside world to show other people what they were seeing, and then establish a sort of communication link in that way.
Wow. So, I mean, remarkable, because I guess, just at that human level, it's not just adapting to a technical problem as well. It's just, it is an emotional backdrop to all of this. In a way, I found it, quite impactful, not just from the scientific results, that were hinted at yesterday, but also just in terms of achievement, what it represented, that, in spite of it all, things have kept going and kept moving forward. And I think there was a hopeful dimension to it all, to seeing those results, knowing what had been happening in the background. I wondered if that was a feeling that you shared as well.
Absolutely. I think this really shows the resilience of this entire big team. It really shows that it's only a big team that can do it together, but it also shows that these people worked incredibly hard in a situation where most people just struggle to somehow spend their days. I mean, there were colleagues of ours in Spain that were under complete lockdown. They couldn't even leave their house for over 50 days. Some of them have, let's say, 4 young children that had to be homeschooled. And I mean, most people were already, let's say, in outside their comfort zone, having to combine family life and work in a normal setting. But this was not really normal work where you do something that you know exactly what to do. This was really like unprecedented activities where you had to improvise on a daily basis, do extra work late in the evening on the weekend, and you never really knew how long it would take. And the fact that these people really worked so well together and so hard that they managed within a few weeks to pick up the pace and then in the end finish at the same time that had been planned for years before, that is really amazing. And that really, I mean, gave me a lot of additional respect to the teams, to everyone, because it's not sufficient if a few people can work that way. It only works if everyone can sort of chime in and do that. And I think people were also almost completely, well, let's say, calm and confident that they could do it, but also very forgiving with respect to the constraints of others. Because sometimes, I mean, maybe you've had a terrible day or you felt you just couldn't cope with everything, and people were really trying to make it work for everyone else. So I think that really impressed me on a human level. I think this is something really that will stay with me for the rest of my life.
So Miho, how for the scientists in the outside world, of course, I mean, there's as Daniel said, right? I mean, under extraordinary circumstances, people pull together to make this happen. But there's also, there's a sort of a sense. I hate to say that people feel cheated, right? I mean, because some of the aspects about doing these amazing things is then being able to celebrate with your friends in ways, and we've all kind of had to learn to put all of that off. And so how has that been in the scientific community? What have you done to compensate? Have there been lots of virtual Zoom parties with champagne glasses and so on?
No, not really. Not really Zoom parties. There were a lot of Zoom calls though. But yeah, I mean, I think it's the and Daniel talked about it very eloquently. The fact that we were all together for the launch, and for me to share this moment with all my colleagues and all these colleagues that we've been seeing each other, I would say 4 times a year between all the the workshops and the instrument team meetings that we have, and I remember seeing the launch, holding hands with some of my colleagues, and then suddenly being after I arrived back in Paris, just being in lockdown and not being able to share the different milestones. But there have been we have on the scientific part, we have a weekly meeting And I have to say that for me, that really kept me going in difficult times during the lockdown. I think we were, at least for me, I was kind of eagerly waiting for these weekly meetings, while on normal times I'm just like, yet another meeting. But to be able to, even in a virtual space, to be able to share, and also to have the different milestones. The commissioning for our instrument went really, really well. To see the first light data, when the emails were exchanged and everything. There was just all these things, even though I couldn't celebrate physically with other people, to just have these times, for me, really kept me going when work was difficult or the time was really difficult. So in a way, I don't really feel cheated. On the contrary, I felt like it was great that I had this to keep me going.
I was wondering if you could elaborate a little bit on that, actually, because Mark said something right at the top of the show, which I guess not a lot of people immediately realize is we're seeing these startling images for the first time yesterday, in the wider world, but they came in a few weeks ago, right? Just like when you first described the emotion. I mean, because I guess there has to be a pregnant pause, right? Where it's just you're waiting for it to come in and all that. I mean, just what is that moment like? The moment that you saw one of these images for the very first time.
I guess maybe the first one is relief. Like you're relieved that the instruments are working well. You're relieved to see the sun, and it's what you would expect. And then there's an interest as well. You're looking at all the details and, oh, what am I seeing here? Is it something I would expect? And then we exchanged, in my team, we exchanged the first EY images that we got that were presented yesterday. And yeah, there's this excitement. And but again, I think in a way, the fact that I wasn't with my team, and I was just alone seated in front of my computer, I kind of felt like, oh, I wish you could high five and really share that. And then I guess there's also impatience, because you want to show it to the world. But of course, you need to prepare the press release. And I didn't see also so I saw two different sets of data from two different instruments, but I didn't see the whole set of data. So there was impatience for me to see what the other instruments had seen, and also impatience to show the community, because a lot of people are interested in the data, but they didn't get access to when it arrived, and also the entire world.
Yeah.
Yes.
So that brings me a question that I asked you again just before we came online, and you weren't with us at that point, Daniel. I've already had questions from people saying, when can I get hold of these data? When will they be in the archives? Because again, it's that sort of sense from the solar community that the SOHO and SDO images are there. People can, and it's not just scientists, it's people in the amateur community that want to do things with them. But of course, with these instruments, which are new and are being calibrated and checked out, and also you've got science teams who have been working for more than a decade to prepare instruments and prepare scientific cases. I think it's, other people disagree, but I think it's reasonable that there be what we call a proprietary period, so that people can get a hold of the data, firstly to ensure the quality, but also to get the first go at the science. So tell us a little bit about how that process will proceed, data release, and as Miho said, it's important that the team see each other's data, because that's what this mission's about. It's about joining data together, not just my image, your magnetic field. They're supposed to come together.
Absolutely, and that is indeed a big topic of the ongoing discussion. The ultimate goal is really that data wants to be free. I mean, ultimately, what we are there for, as a space agency, is to provide the community and the world at large with data that they can look into and get new results from. So that is our goal, and ultimately, we offer the right to the instrument. And the deal is then, in exchange, the data will be free and open to everyone. And there is a certain period initially, and that is on the order is 3 months after people receive the data. So that means any time it spends on board before it can get downlinked, and then they get 3 months to calibrate and validate the data. And especially in the beginning of the mission, that is actually time that is needed, because if you, for example, want to know how hot are these campfires, you want to be precise. I mean, yes, you could look at any image and then just, let's say, get a number that looks right and say, look, they are 5 million Kelvin, but maybe they're not. So you really need the expertise of the instrument teams to to calibrate that correctly. And that is what this so-called commissioning phase was there for. So the EUI team was really amazed me in their openness. They said, well, whoever is interested can work with us even at this stage. I mean, we can't give you the answer yet. These are not scientific measurements yet, but these are the first images. And as soon as we have something that we trust ourselves in, we will give it to everyone else. So that is good. And I think this is the way to go. And I've luckily had good advice from experienced colleagues that were, let's say, roughly my age when SOHO was launched. And they said, look, as soon as people have a couple of sets of data in the can, they will get a lot more relaxed because they realize that the sun shines on everyone and there's more than enough research to do. And in fact, most teams are not hugely staffed. They have probably many ideas, but probably twice as many ideas as they have PhD students or postdocs. So they will want help. And this is, I think, really what it's all about, to foster collaboration and tell people, look, here's the data. People, I think, on average, will appreciate the effort and come back and ask these people for let's say, technical help, and then they can collaborate. So usually that works well. There's a rare exception maybe where someone would just try to get the data and run away with it, but the community is not that huge. So ultimately, I think with the open data policy of previous solar missions like SOHO and SDO, people have really gotten used to doing that successfully. So that is my firm belief.
And so let me just pick up on that, Alex. I think that takes us to a slightly different piece of territory. That's the scientific data. That might be, for calibrated science data to derive scientific results from. But both of you, and one of the, another reason to invite you both on today is that you're both quite involved in outreach type projects, in taking the data, taking the images, taking the science, and then putting them in a form which can be then more easily digested or assimilated or enjoyed. So Miho, tell us about some of the things you're doing, and we'll come back to you, Daniel, in a second about HelioViewer. And so you've been putting together some apps, I understand we were talking about just before.
Yeah, exactly. So what I guess it started a few years ago when I kind of wanted to have an outlet where the general public could experience the data in a different way. So it's not just just images, but how to feel the data. And I created 3 projects. The first one is already out on YouTube 360. It's a VR movie about solar storms. The second one has just been released today on Google Store and Apple Store. Just an app that lets you see the different lights of the sun. So we talked about ultraviolet light, so you can see the sun in these colors, I like to say, and Solar Orbiter. And then there's a third one that is has only been shown to the scientific teams and also during the launch event, which is looking at Solar Orbiter in 3D, so in VR. And so this is more presenting the different instruments and also the scientific interests of the mission, but being fully immersed so that you see it in a different way than what you're used to in like normally in everyday life, I guess. That's what I do.
We'll put a link up to it later on. You said that it's already live, this new app that's there on the Android and the Apple stores. So we'll put a link up to that later on.
Yeah, the latest version is live since 2 hours ago.
Cool. And then Daniel, you've been working for many years on this thing called HelioViewer. So give us a bit of a background to what motivated that and what that does for, not just for the scientific community, well, both. I mean, that's what's amazing about the tool. It works for both the science community and for the amateur community or the interested community.
Mm-hmm. Right. Yes. So this piece of software called HelioViewer, that's something that was started back in 2008. And back then, there was the idea that, well, there's new technology out there that should enable looking interactively at large volumes of data that, let's say, it hadn't been really explored in the context of the sun. And this big new satellite SDO, Solar and Heliospheric Observatory, was about to be launched. And people were saying, look, it creates this huge amount of data, 1.5 terabytes per day, but we can't send it to you. This will just come down. It will be copied to between 3 and 5 places in the world. You can tell us what images you want, and we'll send them to you. If it's more than a few hundred, you might have to send us a hard drive. And we thought, wow, I mean, this is somehow seems like going back to the age where you really like ship things by mail. And I thought, well, there has to be a better way. And a colleague of mine, Jack Ireland, had already started doing a little demo that was a little like Google Maps just for the sun, where you chop up images into tiles, and then you use, let's say, the back then relatively new web technologies to create a seamless zooming and panning experience. And then we used the relatively new and a bit obscure data format called JPEG 2000, which enabled us to compress data significantly, pretty much like the normal JPEG format that everyone uses, but also pack all the metadata of the images in there as well, and somehow implement something like a video streaming on a very specialized level that would allow you to look at data from SDO from the entire mission, even though the science data could not be kept online for more than a few months. We could have a compressed archive of the entire mission, so people could really look for interesting things. And you could find them in this compressed data because compression works actually quite well. And then have, let's say, a go-to place to decide what data do I actually want from the archive before I send my hard drive to be filled with something. And that really worked. I mean, it was really exciting and fun project to do, because it really pushed me out of my comfort zone, because I had to employ, let's say, software developers, even though I'm not a software developer myself. So I needed to be very clear on what do I want, what can be technically done, and how do I want to do this. And that worked really surprisingly well. I mean, better than I thought over the years. And people in the scientific community started using it. And I was amazed that they even started using it for science planning, because they said, look, I mean, I can get these images for every day for different instruments. And then we thought, well, I mean, that's actually exactly what we wanted, that people could combine data from different missions, like coronagraph images from SOHO with images of the solar disk from SDO. And yeah, I mean, that now that people really started to like it, there was also a good, let's say, reason to ask for a little more money to expand it further. And then I thought, well, the next logical goal would be to go out of the, let's say, plane of images into 3D. And that was maybe 7-8 years ago. So I thought the first, let's say, proof of concept would be using stereo images, because these are twin spacecraft launched by NASA that fly at the distance of Sun to Earth, but one ahead of Earth and one behind, and they image the Sun from different perspectives. So we could suddenly, let's say, color a sphere with images of the Sun, and that was amazing, and it really seemed to help people, for example, to get this spatial context of coronal mass ejections traveling into space into different directions. And then ultimately, of course, I had Solar Orbiter in mind, and I thought, well, this is just a milestone. Ultimately, when Solar Orbiter launches, I don't want to stand there and say, look, this is a picture taken from here, and this is a picture taken a month later. They are somehow related, but only a person with a PhD can make that connection. And the litmus test was really when the night before our mission commissioning review, I got the first light image from our wide field imager, which is sort of a fisheye lens looking sideways into the sky away from the Sun to catch coronal mass ejections. And I asked the PI, I said, look, if you have an image, they had just opened the instrument door, said, send it to me. I'll see if I can visualize it together with other images that we have. And it literally took half an hour of tweaking some keywords, and it worked. And you could see the Sun, you could see the stars, you could see Mercury, and you could see data from other observatories just in one family picture. And that's when I thought, okay, this was definitely worth it, because it works.
I feel cheated now, though, because I haven't seen that picture, so you'll have to send that one over. But I was going to ask earlier on, and I think, Alex, we should go back to you, Alex, but just briefly, with this side-on camera, has there actually been the opportunity to image Comet NEO-wise at all? Has that been something? Because I know that Stereo has seen NEO-wise. It may not be possible with Solar Orbiter just because of the current situation in the cruise phase, but is it something which could be done? I
believe it could be done. In fact, I have seen, let's say, numbers that in, well, roughly now, plus minus, it should enter the field of view of the instrument. Now, right now, the instrument is not switched on to take data because, as we said, we had this testing period for the telescopes, and now the main focus is on the in situ instruments because right now we have limited data rate and so forth. After this major push to get everything ready for the beginning of the cruise phase, I've been, let's say, trying to be nice on any single operations person, not asking for more, because I have asked for more than once, and I try to use that, let's say, judiciously and not ask for too much. But if it is possible, then we definitely want to do that.
That's what I like to hear. That wasn't a setup, by the way. We haven't sort of arranged that at all. Just why not? You know?
Yeah.
So, you know, a lot of what's come up throughout this conversation is a very strong sense that, you know, we ain't seen nothing yet in terms of what Solar Orbiter is going to eventually reveal. I mean, you know, the first images we've seen are absolutely breathtaking, but there is more to come. So what's next? Obviously, there's a lot happening behind the scenes, but what can we expect in the coming weeks, months, and years?
I would say that the next really interesting time will probably be in early fall. That's when I expect that the teams of the 4 solar wind instruments that measure particles and fields close to the spacecraft, they should have, let's say, first really novel scientific results. And of course, some of this, well, we need to see really how long things take, given that some delays were encountered due to COVID-19. But that's been our goal, that, let's say, in early fall, we'll share the first, let's say, scientific analysis with the world. And later in the fall, we shall also really make the first sets of in situ data available to the worldwide community. And also there, I mean, this is exactly what we touched upon earlier. It's a detailed trade-off between trying to stick exactly to the timeline that we had in mind and really making sure that the data are fully calibrated, because some instruments really had to, let's say, go through their own sets of issues and let's say learn how to deal with the constraints of the spacecraft. So we'll need to, let's say, fine-tune that to really find a date where we are really confident that the data is good. But then before the end of the year, it will be, let's say, free to the world. And we expect then that many more people will be able to work on it and find new things. So that is the next milestone. And that will continue the let's say, data taking in the space plasma part of the mission for the next 1.5 years. And I would say, given the amazing results we got from our test images just now, I think we have a good case as scientists to maybe gently ask for a little more test time in the next 1.5 years for the telescopes as well. I mean, scientists are always known to be, let's say, weaselly in some ways, and always ask for more. And they would, yeah, let's say, I'm ready to accept that criticism that we always ask for a little more than what is probably reasonable. But that's really what makes us scientists. We want to, let's say, push the limits a little bit and see what we can do. And
come on, Daniel, it's not a bug, it's a feature. It's what we do, right? I mean, we wouldn't be doing if we weren't pushing. But so Miho, just from the perspective of the camera teams, of course, we're not, these images that have just come back were from a distance of roughly half that from the Earth to the Sun, and we'll be ending up quite a bit closer in. So talk us through that and you know, where we'll be with respect to the distance to the Sun and the coming out of the ecliptic, and why that is meaningful also for the imaging teams as well as the solar wind teams that we were talking about.
Well, so yeah, the pictures that we have seen yesterday have been taken at around 77 million kilometers. So just to put things in perspective, the Sun-Earth distance is 150 million kilometers. And ultimately, we're going to get really close, around 44, 42, I think, million kilometers. So a bit less than the Sun-Mercury very distant. And knowing what we have seen already that far away from the sun, the fact that we're going to get closer, we're going to see things in many more details. And personally, I'm really interested to see all these details, but also to have many more data. So yesterday we have seen a set of data, and we have many more to come even during the cruise phase. So we've got remote sensing instruments observation windows next year. We've got 2 at the beginning of next year, and then 1 later on, the second part of next year, and then we enter the nominal phase mission. So we've got all this milestone, more data, getting closer, and then ultimately at some point in the mission, also out of the ecliptic plane. So there are all these things to look forward to. And if I can just say something on my personal level, what I'm looking forward to is at the moment, we're sending telecommands to our instruments that is recording everything that is going on in terms of checking that the instruments are working fine. And for me, I'm just looking forward to start sending science commands to the instruments.
So let me come back to Daniel on this, because I told him I'd ask this question. It came up on social media earlier today. When we get in closer to this 42.5 million kilometer distance, the sun, of course, is brighter. The sun is more intense illumination by a factor of 13. So the spacecraft gets really, really hot on one side. We're not going in as close as the Parker Solar Probe, which everybody knows, the NASA probe. But because we're not going in so close, we're able to take images. They're not taking any pictures from close up because it just gets too hot. So the question that came up on social media was this one about, how do we avoid getting super cooked? We've got this enormously hot object when we're that close up. Parker Solar Probe has a white reflective shield on the front, and people are curious, why is Solar Orbiter's shield black? Surely that's the last thing you want, is to be absorbing all this heat. And we know, this is a coating made by a company in Ireland called Bio, which is actually made out of charred animal bones. So it's not a vegetarian satellite, unfortunately. But tell us, give us a little bit of insight into why it makes sense to have something, a black heat shield, when you're actually going close to the sun.
Yes, Mark, indeed. The simple answer is if you make it black, it can't get any blacker. And that is quite comforting when you know that whatever you do has to work for the next 10+ years. And of course, if you would make it white, that would have advantages because it would have a different, let's say, reflectivity, and some of the heat would just go away. And if you make it black, of course, I mean, as everyone knows, if you wear a black T-shirt on a hot day, you tend to feel a bit warmer. And so in this case, it just happened to be that this particular coating that worked the best in terms of being very adhesive to the titanium foil was black. So ultimately, it's charcoal, which just happens to be black. And this company made experiments with titanium implants for humans, and they experimented with different ways of treating the surface of the implant so that they would bond well with human bones. And one thing they came up with then ultimately inspired this particular coating. And it is not, let's say, a paint that you put on, but it is really ingrained in the surface of the titanium foil. So it's very resilient. It can take a lot of beating by solar energetic particles, by electrons, protons. So that's what made the difference. If it had a different color, okay, we would have taken it. But then instead, we designed the heat shield around that, let's say, feature, and made sure that all the heat that it absorbed would then be radiated away sideways. So in a way, the heat shield is a little bit like a sandwich without the filling. So it has a top layer and then a middle layer that's sometimes called the mezzanine, and then the back of the spacecraft. And in between, it's just being held together by something like titanium toothpicks. So it creates a void in between that then allows the heat that is absorbed on the front side to escape sideways. And that works well, and that has been tested to the extent that we can test it. There's, for example, a big test chamber here at our workplace at ESTEC in the Netherlands, where you use light bulbs of 25,000 watts each from, in fact, IMAX movie theaters that have been tuned such that you can really imitate the sun, or actually two suns, to make things really hot. But what we encounter, as you said, Mark, is more like 13 suns. So we needed to focus that beam and make it really hot, but that focal area was smaller than the heat shield. So we could test it on, let's say, a third of the heat shield at a time, but at least we could validate that on that part it did work. And that's what makes us confident that once we are at perihelion, it'll be okay.
Cool. So I'll hand back to Alex, just noting there's got to be something you've got to use there, Alex. If you make it completely black, it can't get blacker than that. If that's not something that plays into the heavy metal world, I have no idea
No,
what it is.
truly, I was about to say Solar Orbiter, the most heavy metal of all the probes out there. So that's very cool. We're going to have to make some T-shirts out of that too, for sure. So we can't go a moment further without acknowledging all the lovely people who've joined us today. Actually, there've been some wonderful questions coming in through the live stream, many of which have really been answered or touched on here and there. But I wanted to begin with a quick one from Steve, because I'm also curious myself about the life expectancy of the mission. Now, Daniel, you mentioned 10 years. What's the conceivable lifespan of Solar Orbiter?
Right. 10 years is what is called the extended lifetime. So that is a number that the engineers have designed the mission to. And that really says a lot about the way that you do space engineering. They really want to make sure that 10 years is effectively guaranteed, that this is as long, for 10 years, everything should work exactly as planned. Typically, I mean, you usually take some margins to make sure that you can really almost guarantee these 10 years. So if you are lucky and don't get, let's say, wiped out by a huge solar storm that happens every 150 years or 200 years, then there's a good chance that it will live longer. And the two limiting factors are usually fuel and solar array degradation. So with the fuel, I think we are in really good shape because we got this picture-perfect launch by our NASA and United Launch Alliance colleagues that really hit the bullseye in terms of the orbital insertion. So usually you allocate a good chunk of fuel to get the trajectory corrected early after launch, because you never really know whether the launcher will perform completely nominal. And that was just spot on. So that saved us probably several tens of kilograms of fuel, which could translate into operating the spacecraft for another few years. And for the solar arrays, it depends a bit on solar activity. And if the sun is extremely active, it has more energetic particles, and those can over time degrade the solar arrays. But we see from SOHO that even after 25 years, I mean, it's still above that bar where things could start going downhill. So even there, I would say we are in a let's say demanding environment. The mission could experience quite a bit of degradation if there's a lot of activity and we are close by the sun. But I have good hopes that the spacecraft can really survive significantly longer than for 10 years. Interesting.
Great answer. One for Miho. We actually touched on this a little earlier, and some great questions. One's from Sean Doran, and the other from Annabelle. And it kind of overlaps. It's about getting the data. How does the frequency of getting the data compare with the SDO, for instance? And how long does it take for it to reach the Earth?
Yeah, so the frequency, so I think then I can answer that much more clearly. I guess the problem is we have to wait for the spacecraft to get close to the Earth so that we can download the data from the spacecraft. And so that will depend on when the observation windows are and when the spacecraft gets closer. So on average, I will turn to Daniel because he might know that better than me. What's the frequency of downlink?
Well, in the nominal phase of the mission, we have a downlink of roughly 8 to 9 hours every day, or at least 5 out of 7 days. So we have, out of this so-called S-track network of antennas, we have almost our own antenna in Malagüe in Argentina that will receive most of the data. And we have made a case that, let's say, on certain occasions, it makes sense to get additional passes, let's say a second pass from a different antenna on the planet for another 8 hours. So there's, for example, one in Nunosha in Australia. So we will use these extra passes that we have negotiated when they make most sense, because in good orbital configurations, when we are close to Earth, even one antenna is enough to get all the data down. And in other circumstances, it makes sense to use a second one, because then you make sure you don't clog up the system a couple of weeks down the line.
But just give us, so I think there was a kind of two-part question there in a sense. I mean, just firstly, the data rates aren't very high, right? I mean, we're not talking about, not even broadband in your own house. It's nothing like that because of the distance of the spacecraft.
Yes.
So there's firstly that, and the second part, as Miho was alluding to, there are times when we will not be getting data back in real time because the spacecraft's on the other side of the sun. We can't point our radio dishes at the sun and get data back in those times, right? So there are breaks in this continuity as well.
Exactly. Yeah. So yes. Oh, go ahead.
No, sorry. Yeah, and the bottom line is that what we call the latency of the data varies between a day and up to 6 months. So in the worst case, I mean, you can imagine that you take data and it's, let's say, the last on a stack on the spacecraft, and then the data starts flowing down, and then the data that was there first gets downloaded first. And if you are, let's say, the unlucky last bit on that stack of data, that it can take you up to half a year after having been taken until you get sent down.
But then I would also mention the fact that there are different types of data. We have the full science data that we as scientists will want to use, but we also have what's called low latency data. So it's kind of a reduced amount of data and of lower quality, I would say, just so that, first of all, we can check that instruments are still working well, but also because we have to program the observations in advance. We kind of know what's going on at the sun and what kind of targets we want to have. So this data will be lower quality, but also more easily downloadable.
And are they available on a different time scale to the general public? I have no idea. I mean, these are kind of quick look sort of navigation camera in other circumstances, you would call them. Are they available on a different time scale, or do they go into the part of proprietary package?
No, that's a good question. And this is really something where I'm really happy about everyone pulling in the same direction. We had long discussions several years ago, and effectively it's a bit like, I don't know, like with the ring on Frodo in Lord of the Rings, that people said, look, let us all agree to make this data free for everyone right after receipt before we launch, because otherwise I might sort of retract my offer and I want to keep it for myself. And then we said, look, okay, let's do that. And everyone agreed. And so that should actually come out relatively soon. It's just a matter of working out the technicalities. And I think this will be fantastic, because it's like Miho was saying, small volumes of data, to some extent really meant for technical checking, and it will certainly be superseded by science quality data that comes later. But it could be really useful for some purposes, for just like getting a feeling of like what went on. You should see signals from coronal mass ejection. Maybe you could even use some of it to, let's say, get a feeling of the interplanetary space weather. So we'll see what it can be used for, but we put all the mechanisms in place that it will be available to the maximum number of people as early as possible.
And I'll jump on what Daniel has said. The fact that we are working hand in hand with, Parker Solar Probe, but also different planetary missions. And so what's interesting is, depending on where the Earth is or where Solar Orbiter is, the Earth might not see something that Solar Orbiter is seeing that might impact other planets of the solar system. So we can also use this data for other communities as well. And for me, it's kind of great to have this.
Excellent.
Absolutely fascinating. I'm sorry, Mark, did you have a question there?
No. I think this idea of making the data kind of, again, we've done it on other missions where you make the low res data available, and it's not because you're hiding the science data. It just takes a long time to get the science data down. It's more detailed. There are more bytes to be downloaded. And this idea about space weather and triggering and using the quick look images maybe to point other spacecraft and to be able to get observations of things, because of course the coronal mass ejections take time to travel across the solar system. If you've got enough warning, maybe you can do something. In the worst case, maybe you can, turn a spacecraft so that it's not facing in the wrong direction if a CME is going to blast past. It's not that simple, we know, but that trigger and alert thing is something which is important too.
Yeah. So, I just want to ask, just as we wrap up today, because it's been an absolutely fascinating, conversation. I've definitely fallen into the camp of, I think all research is, self-justifying. Just if it's out there, we should be studying it and learning. That's just the fundamental human quality, is to learn. But, in terms of, applications, what is the kind of data Solar Orbiter is going to yield? How will it affect our everyday lives? Things that people aren't always conscious of, like solar flares, solar storms. What might it tell us that will actually kind of improve just the everyday conduct down here on Earth?
Who starts?
Question.
Go on,
go
on,
ahead.
Miho. You're the space weather expert. Go on.
Go on.
Well, yeah, I guess so. What I was saying just a little bit earlier, the fact that we're getting closer to the sun means that we're going to get the data upstream, like very much closer to the source of where solar storms are born, where the particles are accelerated as well. So there's this science link that we're missing at the moment, and that Solar Orbiter is going to give the data. But we've touched on a lot of things. So whether it's getting closer, but also having a different point of view than the Earth. So depending on the position of Solar Orbiter, we might see active regions that are growing before they appear in front of the Earth. So it's kind of predicting what's the dynamics of these active regions, whether they're going to spread out some particles or some solar storms. But again, not just for Earth, but also for other planets of the solar system. So we have seen solar storms that are that are born at the sun and that are not necessarily going in the direction of the Earth, but they might hit Mars. And we also have Mars missions, such as the Curiosity rover, that feels the impact of the solar storms on the surface of Mars. So it's kind of connecting all the dots with all the space missions that we have. And Solar Orbiter, again, is really going to fill the gap by getting closer to the sun, having another vision, so not just where the Earth is, but also above the ecliptic plane. So it really adds a lot of different missing pieces of the puzzle.
So, and to be clear, if I could follow up, because that's a wonderful answer. Space weather affects Earth weather. It also affects telecommunications. Just all kinds of instrumentation. So this is there's an everyday benefit to learning more and more about our star.
Yes.
Please.
Yeah, and I guess that's something that we started by saying that the sun is kind of, we take it for granted, but actually the more we know about the sun, the more we realize that us as a society, we have evolved in a way that we're much more vulnerable to the sun's activity, because we have electricity grids, because we have satellites, and the space weather is indeed affecting the whole space environment of the Earth, all the way down to how currents are flowing in our electricity grid systems, how pipelines can be affected by those currents that are circulating in the soil of Earth. So there are all these things: telecommunications, electricity grids, what more, the ionospheric, the ionospheric state of Earth as well. So all these things that we never think about, but we use this technology every day. So it really does have an impact, not just because it gives us the lights, but also because of the sun's activity.
And I thought I would just give the floor to Daniel there as well, as we wind up, because of course ESA we have a broad-based program of pure research, of applied research. We have the space situational awareness people who are looking at asteroids, but also space weather. So where does Solar Orbiter fit into that? I mean, we wouldn't want to give the wrong impression that it's there designed as a mission to protect the Earth, but it fits into a broader program that we have.
That's exactly right, Mark. One point that I always try to make is that one should not assume that space weather forecasting is something that can be just, let's say, done on an engineering level by saying, oh, I don't really care about the scientific details, I just want approximate answers. But really, space weather forecasting is the pinnacle of solar physics in a way. I mean, you cannot really do that without having understood first what really is going on. And that's how Solar Orbiter fits in. It's not really an operational forecasting mission or monitoring mission, but it will fit in, will have, let's say, the capability of informing us about what is important. And for example, there's, from the Space Situational Awareness Program of ESA, there's the plan to build a mission that will be located at the 5th Lagrange point, which is a sideways perspective to Earth, and it would look at the sun at that part that would then, let's say, a week later rotate into view. So it could, if we can predict at some point the occurrence of solar flares, it would be helped by the fact that we have a preview of a stationary spacecraft that always sees the part of the sun that we will be facing a few days later. And that is clearly something that has a direct operational role. But we need to get there, and we need to, let's say, keep doing the scientific investigations to guide, let's say, the operational engineering efforts.
And if I can zoom out from the solar-Earth connection, I would say that Solar Orbiter also answers the question of how the star magnetism influences the whole solar, so in our case, solar system, but ultimately also star system. And while we are trying to answer what happens for the sun and the Earth connection, we'll also ask the question about how stars and planets kind of, what's the interplay between both? And ultimately we can extrapolate what we know about the sun to other star planet systems. And I think it's especially exciting because at the moment we're talking about planetary habitability in exoplanets. So what we learn with Solar Orbiter will ultimately guide us to understand what other star systems are evolving. So that's kind of exciting for me.
Yeah, definitely.
It's hugely exciting for all of us. And, you know, I've got to say, it really feels like we are just at the beginning of this conversation with you guys as well. And, you know, I think on behalf of everybody, you know, at Space Rocks, you know, we'd love to have you back, you know, as more updates happen, you know, in this truly wonderful mission. You know, it's just so wonderful to see the first results from all that. Mark, any concluding thoughts before we apply our tradition?
No, I mean, I think you said it perfectly. I mean, you know, yesterday was just a taster. It was the very beginning. It's always important to mark, you know, the ending of kind of an engineering phase and saying everything's working. But there were scientific results straight out of that, and I think that augurs really well for this mission. And Miho is absolutely right. We don't have, and Daniel too, both the same topic. We don't have an isolated program. We look at one object and concentrate on it. What's really important about what we do in ESA and with our international agencies more broadly is how we bring it together, because there's so many. I mean, stars are a critical sort of element in the way the universe works, and that interaction with planets here in the solar system and in other stellar systems is really important. But I think, you know, we've got lots of missions coming up in the next few years as well, which are, you know, exoplanet missions, which will learn from this one. So I think there's a great synergy to be had and between all of these things. And we didn't talk about terribly much today, but this whole synergy also, you know, culturally, that what does the sun mean to us as a thing, right? I mean, finally, Daniel, your clear weather has got to me a few kilometers away. So it's now blue skies here. So thank you very much for sending over clear weather and sunshine by the end of the conversation. Maybe we'll get to see Comet Neowise tonight, finally, again, after a week. But yeah, that cultural connection, people associate with the sun. People, it's a thing which is a kind of well, hopefully, maybe not in Netherlands in winter, but it's a constant in our life. It's vital to us. And it's a feature throughout the whole of culture. So I hope we can come back and do a bit more on that and in one of the live events, how the sun is not only a scientific object, but a cultural one as well.
Yeah.
And so for the cultural ending, what we always do on Space Rocks, I mean, it's cheesy as hell, but just, you know, we do it. The Space Rocks hand symbol is the Vulcan salute, live long and prosper. Now, this is always a test.
It's space cheese. Here we go.
Space cheese, exactly. And then rocks. So space and rocks together. If we get that, perfect. Well done, everybody. Alex, how many months have we been doing this and you still don't get that thumb out to the side?
I'm sorry.
Somewhere there. Excellent. So thank you very much, both. Thank you very much for coming on. Brilliant. And best of luck with the rest of the mission. We're all looking forward to seeing a lot more.
Thank you so much for your time.
Thank you so much for having us.
Thank you both.
Pleasure. Bye-bye.
Talk to you later. Bye-bye.